Software-wise, there's a lot going on. Obviously, we're reading sensors, we're interpreting those sensors both for local reactive behaviors and for deliberative behaviors, and then we're also doing data link management and housekeeping as well as safety operations, and the uplink to an OCU via JAWS. That's a little bit much to handle on an Arduino. So what we do is we split that problem into low-level processing on board and high-level processing off-board in LabVIEW. Basically, we assume that the mothership has a processor on board that can communicate. The key thing that we do is take the sensor data and integrate that into a map, and that's what we use for all our high-level processing. And this is an image of one of our early sensor tests where we took that data as the vehicle's rotating, and over multiple rotations we combine it into a local perceptual map. The technique we're using is Sebastian Thrun's histogrammic in-motion mapping. Histogrammic in-motion mapping, where we take the data and use that to push points up or down on a local perceptual grid. And this grid is about a 1-inch resolution. Once we've seen, we do some more processing on that, which I guess I think it's further on, to select a course, and then we generate time-based signals again based on that reference to control the actuator flap, to actually move the vehicles. As the vehicle's rotating, we have inherent self-stability. When the vehicle takes off, if nothing's moving, the natural trim of the vehicle is for it to sit and hover. The flap, it's a Hiller-type flap. If we move that flap harmonically, taking multiple positions within one rotation, we can actually tilt the axis of rotation and get lateral motion in a controlled fashion. So that's what we do. We have a half-fast servo on that flap, and we generate time signals to generate multiple positions for that flap in order to generate control signals to move laterally, also in relation to the time signal. Here's an example from one of our tests of how that works. And this is high-speed video shot at 240 frames per second. You can see what's going on. You'll notice, take a close look at the small flap, and you'll see the position starts to change, and the vehicle will start to translate towards the camera. We found this method to be very powerful, and we can generate very large control forces that way. We had looked at the passive gyroscopic control, the bell-type control bars, and we found the aerodynamic flap to be a lot more effective. For our initial ingress, we want a little more higher resolution data. So what we do is we take advantage of the mothership being 3 meters away from the window, and we use a Puerto laser rangefinder to identify the bearing to the window, and then translate that to, again, a vehicle course in the time domain. To track the vehicle's progress, we again have a FireWire camera. This is all running through LabVIEW to identify where the vehicle is and generate corrections. We keep a 470 nanometer LED on the vehicle as a beacon, and then again we filtered the camera input to provide us with a pretty stable reference. To get between the mothership and the air vehicle, we use 60 milliwatt XP probes. This is using the 802.15 Zigbee protocol, and our calculations show with the 100 meter space and the 6 dB loss, we still have 21 dB of headroom with another 10 dB for fade margin. And we found them in practice to be a very reliable link out to hundreds of meters. Also on the mothership side, we do all our JAWS integration on that end. We have custom LabVIEW code that provides the data link out to the OCU or out to the COP, and follows the current AS4 committee version of the protocol. And safety. This was a big deal right from the beginning for our vehicle, and that was one of our key drivers of the design. We looked at all of the high-speed rotor solutions, and we were concerned about weight with all of them for having to shroud the blades and be able to stay within our weight budget. We found that because of the very large disc area of the rotor vehicle, it was a much better trade-off, because we could keep the tip speed low, we could keep the entire vehicle weight down, and as you see with some other features, watchdog timing, and the independent emergency stop system, we could make a very safe vehicle both for our testing and for here at competition. We believe it's a very safe design. It's the weight of a Frisbee, and with the very low velocities involved, it's very easy to deal with, although we still have large control forces should we need it to avoid obstacles. So in conclusion, we believe the Samurai system is a lightweight solution. It's very robust, mechanically simple. It's highly cost effective. Our vehicle price is below $400 per air vehicle. It's intrinsically safe due to the lightweight and low energies involved. And we believe that this configuration has a lot of promise for indoor flight systems. And with that, I guess we'll ask for any questions.